for inviting me. It is a great pleasure to be here. The first time I'm in Vergata, and the very problem was that when Alessandra said that I want you to speak about orbital dynamics in 4 hours, of course we need 4 weeks at least, but I'm trying to touch a little bit all the basic subjects that have to do with the main mechanisms that we need to understand in order to work on the long-term evolution of either asteroids or satellite orbits, space debris, and so on. So, and the idea is, because I wasn't sure about the background of everybody in the room, that I'm trying to stay in between, something descriptive and something very detailed. So, if it's too little for you, just throw something. If it's too much, maybe throw something more. Anyway, and so the plan is to go during the first hour in a descriptive path, so not too much mathematics, a little bit sloppy mathematics, to describe a little bit the main mechanism and the main effects that have to do with asteroid long-term motion, and then I will start introducing equations of motion and secular theory and resonant theory. Hopefully by the end of tomorrow we're going to be a little bit more involved. So, of course, I don't need to tell you, I guess, that the first asteroid was discovered by Giuseppe Piazzi, and it's now the dwarf planet Ceres. This is an older picture from the Hubble Space Telescope. We expect much better pictures in a few months when the Dawn mission will visit, and this is an observation, actually. We see it moving with respect to the back. Now, as we know, in this plot, which is in scale with regards to size but not to distance, we know that the main populations that interest us are the near-Earth objects in the vicinity of the planets, but basically their main source is the main belt of asteroids, which is between the orbits of Mars and Jupiter. There are also the Trojans on the orbit of Jupiter, and there are trans-Neptunian populations, some of which have a small contribution also to near-Earth space. These are some pictures of asteroids that have been visited by spacecraft. This is Vesta and Petia, again in scale. And this is more or less a top view. It's an outdated plot, but it's always nice for presentation. Top view of the inner solar system, where you can see the orbits of the inner planets. The main belt asteroids in white, Earth crossing and planet crossing orbits here, and you see the 2 groups of the Trojans placed near the equilateral points of the ground. Now, to begin discussing about their orbits, we need the basic terminology, the basic stuff. So let me introduce, as you probably all know, the orbital elements, usually the orbital elements, and the laws of Kepler, which dictate that the angular momentum modulus is constant, and this is the third law of Kepler, written with the mean motion introduced here and the semi-major axis. Now, to describe an elliptic orbit, I need semi-major axis and eccentricity for the size and shape. I need inclination relative to the plane of reference. The 2 orientation angles are the longitude of the ascending node and the argument of the periapse. And the position of the body on this ellipse is given by the true anomaly, which is a non-linear function of time that we don't like. So we frequently use instead the mean anomaly, which is defined, and you can find it either as L or M in different books, as mean motion times time, and this is related to the eccentric anomaly through Kepler's equations. And from that you can relate to the mean anomaly, to the true anomaly. Now you will also see that we use a lot other 2 variables, which are the mean longitude and the longitude of perihelion, which are given like that. So we use longitude that refer to a fixed direction in inertial space instead of anomalies. And in the absence of other perturbations, of course, we have a set of 6 orbital elements, if I include here the time of pericenter passage, that are constants of the motion. So if I see the distribution of asteroids as a function of semi-major axis, we also know that it is not a smooth function. There are gaps and spikes everywhere, and we know that the main gaps are associated with locations which, by the third law of Kepler, there should be a resonance in mean motion between the mean motion of the asteroid and the mean motion of Jupiter. Now, there are also some resonances like the theory 2, where you see a spike in the distribution, so there is some concentration of bodies there, the Hildas, and the same holds for the Trojans in the one resonance with Jupiter. So the resonance is not a synonym for depletion, it could be also concentration, so we need to understand the dynamics in different resonance in order to understand why some of them can hold bodies for billions of years and some others cannot hold bodies for a few million years. Now, the second thing we need to keep in mind is that in terms of the physical structure or the properties of the bodies, there is also some radial dispersion, but in principle, in the inner part of the inner belt, most asteroids are silicates, while in the outer parts, most of them are carbonaceous. So there is a difference in the spectral properties, which actually means a difference in physical. I guess that the main thing that why we would be interested in this school is the connection between the near asteroids and the main belt asteroids. So this is not the real integration, it's a sketch that I did to say that if you had an orbit initially here in the main asteroid belt, then given enough time, it will deform, and at some point the orbit can be crossing the orbits of the inner planets, in which case you might have some risk for a collision. Of course, those of you who are a little bit more into the problems would probably find a mistake that I have in this sketch, right? Which is that I keep here the pericenter constant, which is not correct. But I couldn't draw it in a better way. Anyway, so to start speaking a little bit about the main dynamical phenomena that we're interested in. The first is the phenomenon of secular precession. So you know that if I take the two-body problem, just the Sun and the asteroid is moving in this potential, which is the central potential. And if I plug it into Newton's equation, I get the solution, this is the formal solution, of the vector r and the velocity vector, and because it's a system of three differential equations of second order, I have 6 adjustable constants, which are the 6 elements. Now, if I add a small disturbing force, let's say gravity from Jupiter, and small is indicated by this epsilon here, I try to find a solution. And the first solution that we know is you make an ansatz that the solution you got for the two-body problem still holds for this problem, but now the constants are no constants any longer, they are functions of time. And you try to find these functions of time. So you insert it here, you take into account that the original solution satisfies the homogeneous system, and you try to determine the function. This is Lagrange methods of variation of constants, of course. And let's say in a very rough linear approximation that we will see in much more detail later on average, what you find is that at least there is some precession of the orbit, which means that the orientation angles and also the size and the inclination change in long periods of time, very little, of course. So these are the long periodic variations that we call secular variation, the secular precession, and the frequencies are much smaller than the orbital frequencies. They are of order 1 over epsilon, this epsilon here. So for example, in the solar system, if the mass of Jupiter is 1,000 times smaller than the mass of the Sun, secular precession period should be of the orders of a few thousand times the orbital period. Now the second important phenomena is resonances. So you see here the distribution of asteroids in the semi-major axis eccentricity and semi-major axis inclination plane. And these are actually, each dot is taken from this catalog of synthetic proper elements by Milani, Knežević, and co-workers. And a resonance, of course, occurs when 2 or more frequencies become commensurate, or in general, a linear combination of the frequency is 0. And you can see immediately from the plot that we have important mean motion resonances, the ones that we saw in the previous plot, of course, at the location of the 3 to 1, 5 to 2, 7 to 3, and 2 to 1. And they have a characteristic shape. They are vertical in this diagram, which just reflects the degeneracy of the Kepler problem, where each orbit at a given semi-major axis, irrespective of the eccentricity, should have more or less the same mean motion. And the size and shape of the resonance is slightly modified, and this has to do with what we call the order of the resonance, the difference of these two numbers here. Now, of course, there is another class of important resonances, which are called secular resonances. Taking into account that we have secular precession, so each asteroid has a precession with a given frequency, both in the pericenter and in the node, you can ask yourself whether it is possible that this frequency becomes equal, or a linear combination of the frequencies 0, between the asteroid and one of the fundamental modes of the planetary system, case it's better to say. For example, the mean, let's call it the mean precession period of Jupiter or Sun. Because don't forget that as the planets perturb each other, they also undergo secular precession. So there is the possibility for such relations to hold, in which case you have a strong secular resonance. The timescales on which this resonance was are very different, but the effects can be the same. So if I plot now the location of the main resonances, mu5, mu6, as we call them, mu6, there's no mu5 in this case, and mu16 for the inclination, you see, for example, that they more or less fit the borders of the eccentricity inclination distribution of the asteroids. Now, there are other classes of resonance that you may have heard. There are other types, the quasi-resonance, there are mixed resonances, or secondary resonances between the libration frequency of an asteroid period and its pericenter. There is also the possibility that secular resonances are not just outside the distribution, but they occur also inside the main motion resonance, so you have double resonance. But the basic idea is the same. What you have to keep in mind for the moment is that the lower the resonances are, the stronger, and they are, to a first approximation, the ones that interest us are these big resonances and these ones, the linear secular resonances. Of course, if we go to the near-Earth space, the dynamics are much more complicated because the bodies can have close encounters with the planets. So you add that on top. Now this is an old plot from a review paper by Christian Froslet, Orbital and Bot, I think, where you can see now, if we move towards the region of the planets, that there are bodies that, if inserted in the main resonances that I showed you before, would keep more or less constant the semi-major axis and not the pericenter as I did in my sketch. But the eccentricity will grow. Given enough time, the eccentricity can be such that the orbits are crossing the orbit of Mars, or even more, the orbit of the Earth. And depending on time and favorable conditions, they can actually be extracted from the resonance, so they can wander in space here, or even, as Giovanni Valsecchi would tell you, they can go up to eccentricity 1 in very short time and become sun grazers. Now, many of the bodies that actually escape from the main belt become Earth crossers, but stay outside 2AU more or less, which is the outside region of the near-Earth space. Okay, and these have a short dynamical lifetime, because either the eccentricity goes to 1 and they follow the sun, or they actually are captured in an encounter by Jupiter and they are actually shot away from the system. But there is a fraction of bodies, mostly coming from the nu6 and 3-1 resonance, so the inner part of the belt, that can actually be extracted from the resonance when they cross the orbit of the Earth and start wandering, having repeated encounters, more or less along a line of constant, this which is called the Tisserand parameter. It's an approximation of the Jacobi integral. And they roughly conserve this parameter. But of course, if you have many planets and you have encountered with many planets, this is also a relation that doesn't really hold. There is some diffusion in this parameter. And the dynamics are very complicated because for some time you can wander along this curve, then you can get trapped in some resonance, then you can go out again and so on. And this can take very long. There are evolved NEAs, as they're called, which can last there for tens of millions of years. This one, for example, is 20 million years. Now, for example, we also have some new results on that, about possibility of having NEAs from the Tuts-1 mean-motion resonance, which is far out in the belt. And we know that there are some asteroids in that resonance that we consider stable for a very long time, but turns out it's not that stable. So there is the possibility of having bodies that reach the eccentricity to become a crosser, survive there for some time until Jupiter kicks them out, and a very small fraction of these orbits can actually enter into the evolved NEA region. This one stayed there for 50 million years. And the time scale of these bodies is not as short as we thought in the past. It's a bit longer than 1 million years, so it's not unimportant. Now, I will speak a lot about mean motion resonant probably tomorrow, so let me do a rough sketch here of what I want to present. I'm not sure if everybody is familiar with the Hamiltonian formalism, but I'm going to go into that in the next hour. But if we sit on the restricted three-body problem, so we have a sun, a planet, and a small asteroid whose mass tends to 0, then we can write down the Hamiltonian function that describes the motion of the test particle. This is a Keplerian Hamiltonian, kinetic energy per unit mass and the potential energy with respect to the sun. And this is the perturbation. This is the mass of the perturbing planet, this is the inverse of their distance, and this is the so-called indirect term that comes from the fact that I've written it in heliocentric coordinates, so in a non-inertial reference frame. This function is actually very well known. It has the name that you probably all heard, that it's called the disturbing function. And if we want to treat the problem in orbital elements, we have to transform from Cartesian coordinates to orbital elements through the usual transformation. Now, if I do that, let's say, and I write it in elements, this term gives just this result, which is well known, and the rest can be some sort of a Fourier expansion, with the coefficients here being in general power series of the eccentricities and inclination. And here you have linear combinations of all angles. Here I kept only the mean longitude for the planet. Now this angle, this term, can be critical in the following sense. If I take each of these terms separately and I take the mean value for some time which is much longer than the orbital field, then because this has a frequency which is of this order and the rest is order epsilon, the mean value is going to be 0 because it will have fast oscillations over this period. It will cover the whole area between 0 and 2 pi and essentially will give you 0. Except for the case where this frequency is close to 0. So it is a much longer period there. And this happens when the mean motion satisfies this ratio, or by Kepler's law, we are at one of the resonant locations that I showed you before. In that case, this average will not go to 0, and the term will be important or dominant. Again, this is a bit sketchy, of course, in terms of mathematics, but I want you to understand the main idea. The main idea is that out of this function, the terms that depend on the mean longitude evolve fast, so on average, they may give nothing, unless some of the resonant conditions are satisfied. In that case, we can show, and I will show tomorrow, that, for example, in the simple approximation, the planar elliptic three-body problem, so I have Jupiter on a fixed elliptic orbit, and an asteroid moving on the same plane. Then, for each combination of integers that satisfy a given resonant ratio, there are q plus 1. Q is what I told you before, the order of the resonance. There are q plus 1 terms that are important in the disturbing function, and you can do a series of transformations to make the Hamiltonian take this form. So if I did not have the sum here and I had a single term, let's say I isolate one of these terms, this is simple Hamiltonian which gives pendulum-like dynamics. So if I see it, if I look at the phase space, this is the angle, and this is the momentum conjugate to it, and I should have orbits that librate in the angle, and orbits that circulate, and in between there is this critical curve, which is called the separatrix, that actually denotes the size of the resonance. As I had here 2 degrees of freedom, if I have only one term, I have only one combination of angles, so essentially the problem is integrable, which means that either one of the momenta, depending on what I choose here for p, or a combination thereof, is actually an integral of motion. However, if I put all the terms in the expansion, then I have terms that differ very little in phase space, so if I would see them separate from each other, it would be as if I had several separatrices, so different, let's call them sub-resonances, although I don't like really the term. They correspond to the same mean motion resonance, but different combinations of the perimeter. And they are very close to each other, of the size epsilon. And depending on the weight of the resonance and their distance, you can show that these, let's say, separatrices of the individual resonance should somehow overlap, and they can overlap either to a great extent or to a small extent, depending on the size of each resonance. And this gives chaotic motion, but with slightly different characteristics. For example, in this case, where you have almost complete overlap, you have a small, relatively small chaotic band, and the motion can take several vibrations before managing to escape outside the resonance, then come back, and so on. While in the other case, where you have the separatrices almost touching each other, basically the orbit can wander here. We will see the two different modes later. This is not, of course, the only mechanism by which you can have chaotic motion in the solar system or in that, but it is one of the primary mechanisms, at least for the so-called high-order resonance, which we typically don't care a lot about. They are not indicated on that plot, they are in here. But as our colleagues here, Andrea and the others, can tell you, they are important in the sense that if you go and integrate the orbit and you look into that, it's a chaotic orbit. So you want to understand what happens there. And even if a resonance is small, you can have, over long enough time, the phenomenon of chaotic diffusion. Now, I'm just showing again a sketch. Let's say that this is the resonance, semi-major axis eccentricity. These are the borders of the separatrix, which is a function of the eccentricity in this case. And let's say there is another small resonance with the same in-motion ratio, but different combination of perihelia that is inside. The two are apart by size epsilon, and they form sort of a modulated pendulum. So two pendula almost on top of each other. Now, if I kept only one of these terms, that integral of motion that I told you means that essentially there is a function of the eccentricity in semi-major axis that should stay constant, so the motion takes place along a curve like that. But if I keep both of them, then this integral doesn't exist anymore. It actually breaks, so you have some sort of diffusion that takes you from one of these curves to another of these curves and back and so on and so forth in a chaotic fashion. Now, we frequently use, or I would say abuse this term, because diffusion has a very special meaning in physics, as you know. But we use it to describe, in general, long-term, small-scale variation of some sort of proper element. And that's a big discussion we're going to have here. By which I mean some action of the dynamical system that actually is close to the real motion. Okay? For example, if my system, the Hamiltonian that I showed you before, I believe it's a good approximation of the real motion. If it is integrable, then the moment of this integrable system, the actions of this integrable system, can be called proper elements. Okay? Although it's a terminology we don't use frequently for resonances, but I will get into that tomorrow. Now, if you want to see a real example, this is from a work that I did together with Zoran Knežević and another colleague. This is the case of the resonance that is called 5 minus 2 minus 2. It's a combination between the mean motions of the asteroids Jupiter and Saturn. It's around 3.17 astronomical units, and it's an area where a small asteroid family known as Veritas resides. And we know from many works, starting from the works of Milani co-workers and others, that these orbits are chaotic on a relatively short, for our time scale, relatively short. Now, if you take a bunch of orbits, a bunch of test particles, and you place them there, indeed you see that this function, which is supposed to be an integral of motion in an integrable approximation of the resonance, actually diffuses over time. So the mean square displacement, which is this curve, is roughly proportional to time. Okay? So the orbits go away in eccentricity over long enough time, and the family should be unrecognizable if it was too old. On top of that, as if the conservative dynamics are not complicated enough, there is a new, relatively newly acknowledged phenomenon that is very important. for asteroid motion, and this is the Yarkovsky. Basically, what happens is that an asteroid that moves around the sun and at the same time spins about its polar axis has, of course, a finite thermal conductivity and a finite dimension. And as it rotates, it absorbs the maximum solar radiation in the noon direction, and until thermal equilibrium is again satisfied, it has already turned to a new direction. So there is a recoil force which has a tangential component, and therefore the semi-major axis changes. So this depends on the dimensions of the body, on the thermal properties and the rotational properties. So it's those that spin up go away, those that spin down come towards the sun. Roughly, an average value that is frequently used in numerical computation is 3 × 10⁻⁴ AU per million year for a kilometer-sized body, and goes down with the diameter, and effectively stops at around 10 kilometers. But this is very important for us because it is the main mechanism by which bodies of this size or smaller, let's say between a few tenths of a meter until a few kilometers, are transported to the near-Earth space. This is from Yarkovsky, and essentially shows that, for example, the asteroids that are here drift because of this phenomenon in semi-major axis in both senses. It takes about 10 million years to enter either one of these very powerful resonances, and then in a few million years they develop, 1 million years more or less, they develop Earth-crossing orbits and they become NEAs. Given this background, you can understand how people are working to make models of the NE orbital and size distribution. This is a recent result by Trojans and compiled on the data by Alan Harris. That basically what you do is you identify the main dynamical sources, 3-to-1 resonance, the nu-6 resonance, the 5-to-2 resonance, and so on. You put test particles in there and you track their motion for millions of years until they enter the Mars crossing region or the Earth crossing region. Depends on how you want to make the statistics. Then from then on, you take these bodies, let them evolve into near-Earth space, and then you measure the mean residence time in each little dot, each cell of this space. So you have the mean residence time in the cell. It's easy to compute also the collision probability from each cell. And you have the relative contribution of different sources. You put weights and you try to find the coefficients such that your distribution matches the observed distribution, at least down to some limit. So you can have a plot like that, which tells you that this is the theoretical, the blue, orbital distribution or size distribution of NEAs, and the red is the observed. Of course, here it's the limit. We cannot observe yet much smaller asteroids. And you can have an idea of what is the size distribution and relate that also to impact probability and impact energy. Now, this is a description about today, and I will spend just a few more minutes to discuss the past of the solar system, so-called era of ancient bombardments. There is enough evidence that the inner solar system, not only the Earth, has suffered intense bombardment during the early phases of solar system evolution. And the results are still visible on the Moon, the big basins, not on the Earth, because weather and geology are good enough in 4 billion years to erase the main points. And for example, one of these is the so-called late heavy bombardment period, which ended up around 3.9 billion years ago, and supposedly had an impact rate which is at least 1,000 times higher than the current, which requires a total mass of small bodies about 1,000 times the current. And there's a question of where was all this mass and why it took some time actually before it struck the inner solar system. Now, the general idea is that the reason for that is the so-called planet migration, which means that we assume that we have good reasons to assume that the orbits of the planets themselves were not in the same place as they are now, at least for the giant planets, and that they had to more or less move into a more relaxed configuration, which is what we observe now. And essentially, if you assume that the belts, or let's stay on the Kuiper, that the Kuiper belt was 1,000 times more massive than current estimates, there's enough mass there to have a decent interaction between the planets, and the exchange of angular momentum can lead the planets to radially migrate. This is an old sketch from a Nature review on Rodney Gomez paper, who first showed that during this epoch, as the planets move around, you can populate by some special populations the galaxy. Now there are, in general, two models, let's say, or two modes of migration that one can assume. The original, coming from Malotra's original idea, is the so-called smooth migration. So basically the planets were closer to the sun than they are now, but not that close. And they interact with the heavy disk that is outside, and they slowly move into new orbits in a more relaxed configuration, which is fine. Of course, it can explain many things, like your Pluto, roughly, or the eccentricity distribution in the asteroid belt, and so on. But there are things that cannot be explained. Now, a few years back, we worked on this problem, and we found out that there is a different sort of evolution that actually we like more because it's more fancy, or because it explains more things. Let's label it a chaotic evolution, which basically means that if the planets start closer to what we previously thought to each other, there are enough dynamical triggers that could induce an instability in the orbits that it's only temporary, because as the planets become unstable, meaning their orbits become very eccentric, they penetrate the disk, and the disk actually exerts dynamical friction on them and stabilizes the orbits on a new distance from us. The reason why we like this sort of model here, for example, is an instability that in this simulation is induced because Jupiter and Saturn start interior to the 2-to-1 mean motion resonance between themselves, and as the planets move, the Saturn crosses the 2-to-1 resonant line. This induces some eccentricity in the orbit of Saturn, and then by secular interaction, it induces eccentricity to Uranus and Neptune, and because the planets are close to each other, their orbits start to cross. But this instability dies out because of the disk, the massive disk of particles that is dispersed. So the reason why we like this, which is now called the NEAs model, is because it explains better the current orbits of the planets in terms of eccentricity and inclination. And also, it agrees more or less with the main constraints that we know for the late heavy bombardment, meaning that if you had a very small rate of collisions between small particles and the Earth in the past, when the instability sets in, you have a large spike in the impact rate of bodies. Now, one can ask whether the distribution of asteroids that we see today can be a good criterion to discriminate between different types of population. The answer is yes, for the most part, in the sense that if this is the current distribution of asteroids in some major axis and inclination, and I'm speaking only of asteroids larger than 50 kilometers in diameter, so not to worry about Yarkovsky effect or small family members and so on, then I can try to reproduce that starting from different initial configurations. Let's say a flat disk or an excited disk, and I make the planets migrate either slowly or fast, either smoothly or chaotically. And then you see that the resulting distributions are very different, and that this one is a much better match to the real one than this one. Okay. And this is, and I'm not saying that this is because of the chaotic part, this is because of the time scale. If it's much faster, it's easier to end up with this, assuming that the initial inclination distribution was also quite hot. So this is a paper we did with Morby several years ago that suggested that probably the inclination distribution in the asteroids that we see now could be primordial in the sense it predates the era of planet migration. It's very difficult to reproduce it out of this. Now, if you see some snapshots of this evolution, this is actually from a later paper by Nesvorny and Bukurisky. And you see here the planets, the major planets, the giant planets, and the disk of particles that is about 1,000 times more massive than the Kuiper belt is now. When this ability sets in, the planets are inside the disk. You don't see them, Uranus and Neptune here. And the disk is dispersed everywhere. Some of that part actually ends up on the Earth and the Moon. And given enough time, the disk completely disperses. You can see trapping of particles in the mean motion resonances with Neptune, temporary. And at the end of the simulation, you end up with the planets in their good orbits. Some relic which resembles the Kuiper belt and the scattered disk of objects includes a bunch of Plutinus here in the 3-to-2 mean motion resonance with Neptune, and other stuff, of which most interesting is Neptune Trojans. So there is some mechanism of capturing also bodies during this unstable period, which is, you can call it chaotic capture, because it's not the standard theory of capture into resonance that we know, in the sense that you have a planet which is on an eccentric orbit, okay, and basically moves chaotically, more or less, and particles that are also moving chaotically outside. But because the eccentricity of the planet is large, the mean motion resonances with the planet are big, and they have a rather large chaotic domain. So chaotic particles from the outside can enter the chaotic sea of this specific resonance. They are connected. Okay? And as the eccentricity of the planet goes down, the resonance shrinks, and the chaotic band also shrinks, and the body is captured in a more regular way. Okay? So this is, for example, the mechanism by which you see particles being captured around Neptune's orbit in this simulation. This phenomenon is not of much use for us now when we discuss the current orbital distribution in the evolution. I just wanted to present it in order to have a more complete description. And this brings me to the end of the descriptive part, let's say, of the talk. Now I know that I have, how much time, Alessandra?
5 more minutes, but
you want me to take a break?
Some questions.
Okay, let's take questions here, and then we can continue.
If you have questions, yes, please.
I have a question that's always puzzled me about the Nisman lecture.
Please.
From my understanding of at least what was published in the original paper, in a number of simulations, from what I understand, the model couldn't account for the final situation of the large planets at the moment. A number of simulations failed to deliver the planets where they are. So that suggests some level of fine-tuning in the initial parameters that go into determining the evolution of the system. And I was wondering if you could comment on, let's say, a global look at all of this, what the level of fine-tuning is that you need to achieve any of this, or whether
This is very nice. This is very nice. First of all, there is no fine-tuning in the sense that you're saying, in the sense that the different parameters that were used are not that different. It's a small space of the it's a small fraction of the parameter space explored, and basically the statistics by which you have the planets in the good location, or a little bit inside, a little bit outside, or you use the planet, is just showing you that the system is chaotic. Now, the fine-tuning that was there in the first and original set of paper was that if you want to get the time scale correct, you have to set up the disk in a specific way. Okay? There are colleagues who have made comments like, it's like putting a pencil here, and if I put it a little bit like that, it will fall, which I don't really agree. But let me say that in the following papers, especially the last one that we published, I think 3 years ago, this problem is remedied in the sense we show that if you take into account properly the self-gravity in the disk, the time scale more or less is unique. There is a barrier, the 3 to 2 resonance with Neptune, and if you have bodies to start with, inside that, the time scale is of the order of 100 million years. If you go outside that, the time scale is of the order of 500 million years, because it's the time at which the disk, due to self-gravity, injects bodies in the resonances with Neptune. Okay, so it's different. Now, the problem of fine-tuning is funny because a couple of years ago, a colleague, Konstantin Batygin, told me that he has actually listened to a radio station in the United States, a religious radio station, that, have you seen this nice model? It was a talk between 2 guys making the show, and said, well, it's proof that there is intelligent design. That was the outcome of the discussion, because it's so fine-tuned that it has to be intelligent design. But I don't agree with that. So to cut the long story short, there is no fine-tuning because the basic part of the time scale has been solved by requiring that the particles that encounter the planets are not to start with in the unstable region. They are in a relatively stable region, and it's self-gravity that has a specific rate if the mass of the disk is given. Okay? The second part has to do with the initial condition of the planet themselves, which in the original paper was a little bit sketchy. But we realized very soon after that if you take into account that before this time there is enough gas in the system, and there is gas-driven migration to planets, then the initial configuration most likely is a multi-resonant configuration of the planets, and there are only 2 or 3 that can survive after this gas-driven migration. So I don't think that it's that much fine-tuning.
May I make
Please.
a almost philosophical comment? Please don't forget that we have a sample of 1. So
Yes,
we have to
exactly.
be careful in saying this is unlikely, because well, we are observing 1 system, and this system could be special. Why not?
There's the anthropic principle that Andrei is saying.
So, as an example, the fact that this system has been able to survive in planet's stable orbit for 4.5 billion years is a necessary condition for us to be here. This could be rare. How do you know?
Exactly.
On that comment, of course, that's changing. The landscape's changing now with Kepler data, other. So, how, reflecting on that fact, how quickly do you think we will be able to extend what's known about this to be able to reflect on those systems and use that data to more or less constrain what's going on here?
Well,
But about Kepler, there is a planet with 4 planets in a 4-body resonance, about what we are seeing in initial resonance state. So
yes.
the examples with resonance are increasing dramatically.
Exactly. And if I'm not mistaken, there are also data about young systems which show extensive activity in the sense of production of dust, which could mean sort of bombardments, or if it's not formation. Okay? And I'm not saying that this is the rule, but it's not easy to differentiate with, or to say what is typical, because as Andrea said, we have an example of 1, and that's it. And on the other hand, if you go into the simulations, there are too many parameters to explore, and the behavior of the system, you change the masses a little bit, or the order of events, well, changes completely. So I prefer to stay into this configuration, these masses, and maybe this order as well, and then we can discuss about the statistics on this system alone.
But if I may make a comment, it's perfectly okay.
We have to, sorry, Andrea, we have plenty of time later, also during your lectures, but let me give 5 minutes now to the people, and then we will resume, and
Sure.
we will make all questions at the
Sure,
end.
sure,
Okay.